in hidden dimensions, and the sort of two sinus turns in one dimension less.
That's what I
showed
showed.
it. Very good. I see. Okay, good.
So I'm going to follow a different route, an indirect route, which is a bit more theoretic and it's more based in principle. And it's the following thing. We have this first order formalism in which we have E and O. And the Lorentz transformations appear here as gauge transformations. And this omega, this spin connection, is actually a gauge connection, a Lorentz connection for these gauge transformations. But the field line is not. The field line is a vector. The transformation laws for these are very different. So we have a theory which is a gauge theory for the Lorentz algebra, but there is also an additional theory. There is not only a connection, but there is also a vector. And there were two persons called McDowell and Mansouri who thought that this was not nice enough. That it would be nicer to have both fields, the field line and the spin connection, as components of a larger connection, for a larger algebra. So to have gravity as a pure gauge field with only a connection, nothing else. And the reference for this So far what we got, we can think of it as this. You can say that we have a one-form Lie algebra value connection, A, this is the spin connection, and these are the Lorentz generators. I'm going to use this one. And why does it make sense to write this? To produce this complicated object. This is a one-form, this is a Lie algebra generator, this is the combination of the two. Why does it make sense to write this? For instance, in gauge theory, you have the field strength. If you're using this language, the field strength is the exterior derivative of A plus A squared. Are you familiar with this? This way of writing it? It's equivalent to the usual way, but it's using differential forms and differential forms that take values in a Lie algebra. So if this was a differential form, an ordinary differential form, A squared would be 0, because one form squared is 0. But this is no ordinary differential form, this is a differential form that takes values in a Lie algebra, so it doesn't commute with itself. And if you compute the field strength for that A, you found this. So this field strength is the Lorentz spirit. Homework. Show this. Let me give you a little bit of hint how to do this. A squared is actually this is not zero because and so you take the one forms out. And you use this algebra here, and this contracts the indices in all kind of crazy ways, and the thing you find is this. So actually this is what you have to prove. And when you add this to this term here, you get the Lorentz curvature. So it actually makes a lot of sense that this field strength is the curvature. But it doesn't stop there. This is, it's hard to read, but it's very simple. So in gauge theory, a gauge transformation and infinitesimal gauge transformation, you can always write like this, like some covariant derivative of a parameter. And this covariant derivative is defined in this way. Here you have the connection acting. And this parameter takes values in the Lie algebra also. So for instance, in a Lorentz gauge theory, this lambda would be just that. And if you compute this for the spin connection, you get this. And this is right. This is the transformation law of the spin connection under an infinitesimal transformation. we showed in the last class. We showed that this was the transformation law for the spin connection. I'm hoping I have the indices right. If they are not right, please tell me. Maybe there's a mistake here. Maybe it's like that. Oh, here it is. So now, if you consider this to be an infinitesimal Lorentz transformation, so you have the identity plus something small, then this turns into this. So it's actually the same thing. So what I have written here is what a gauge theory for the Lorentz algebra would look like. The gauge field is the spin connection, like this. The field strength is the Riemann curvature, and the gauge transformations are what you expect, are the transformation laws for a connection of the Lorentz algebra. And the question is, can we now include the field by as another term here in A? That's the thing we want to see if it works. So that's the idea. To think of the field bind and the spin connection as different components of a single connection. And for this we need to enlarge the Lorentz algebra to include extra generators, which I'm calling PA just to give you a hint. And well, like this. And these extra generators have to form a new algebra including the Lorentz generators. So besides J, we need JP and P. And this cannot be anything because we need to satisfy one constraint. a Lorentz transformation in this language, and we need that when we apply this to the field bind, we get what we want. And so, since we need this, we cannot put anything here. The algebra has to be something very special. And the rest, you can see that to get that, you need the following. So we need that this generator P is a Lorentz vector. And if it is, then we can guarantee that this will work. So I think maybe we make some short break so you can relax a bit. So it's 7 o'clock. What about coming back in 15 minutes?